It's a great pleasure to be here and talk to you a little bit about the importance of water for planet formation. To start with, as most of you probably know, planets form basically in a diagram like this, so to say. So we start with a gigantic molecular cloud, 20,000 astronomical units in distance. Then as this cloud slowly starts to collapse by gravity, we start to form protoplanetary disk around it with an envelope. Material that goes in can actually be thrown away during these vertical outflows, these jets. And then in the end we basically have a protoplanetary disk that consists mainly of hydrogen and helium, but to a small fraction also of dust. And for us, dust is basically everything that is not hydrogen and helium. So we're very simple-minded people in that respect. And then inside of these disks, these small dust, micrometer-sized dust particles can accumulate and form final planetary systems. So that's the framework we are working on. And then this talk I will focus on these last two stages where we have a protoplanetary disk and we try to understand how these disks can actually form planets. So we can actually first, I want to talk about the birth environment of these planets, the protoplanetary disk. So this is an older picture from the Hubble Space Telescope of the Orion Nebula. You see here we have some small protoplanetary disks. So this picture I think is like 15, 16 years old. So I already used it during my PhD thesis some time ago. But this was the best that we had. But you can already see some small structures of these objects. But in recent years, nearly 10 years ago, the ALMA came online, so the Atacama Large Millimeter Array in Chile. And this is an amazing machinery because suddenly we can observe protoplanetary disks in this amazing precision. So what you see here is basically one of the first images that was done with ALMA of the HL Tau disk. And what you see here is the thermal dust emission of millimeter-sized grains. And what you see here is the protoplanetary disks. You see these bright rings and these dark gaps. So bright rings would indicate we have probably more material there that can actually emit in the millimeter wavelengths. And these smaller, these darker gaps would indicate we have a bars of these millimeter-sized particles. Additionally, you see this is the size bar. So this is 14 astronomical units. You see this disk is very, very large, especially compared to our own solar system, where Neptune is around 30 astronomical units. As I said, these disks, they consist of gas and dust. So these dust particles make about 1% of the total mass of the disk, and we can only use the dust to first build the terrestrial planets, super Earth, so also the cores of the gas giants. So we have to understand how these disks can form planets. On the other end of the spectrum, we can actually also observe the planetary systems. So this is the HR8799 planetary system. It has 4 planets. In this case, so it's a direct image system. It's one of the few direct imaged planetary system. You see here the size bar of 20 astronomical units. So the system is actually gigantic. So we overplot here Neptune's orbit at like 30 astronomical units. And you see the outermost planet, this planet B, actually sits at like nearly close to 70 astronomical units. These 4 planets in itself, they're also very massive. So this is the mass estimates of these planets in units of Jupiter masses. So these planets are 5 to 7 times the mass of our own Jupiter. So in that sense, it's a very upscaled planetary system. So this is of course the bigger end of the planetary systems that we can observe. What we are mostly interested in is actually the systems that are very, very close to the central star that you of course don't see in this picture because the stellar light, as nice it is during the night sky, it's very annoying if you want to observe planets, especially close by. So we actually have to use a coronagraph to basically take away the stellar light. So with this method, we cannot observe anything that is very, very close to the star. In this case, we then have to rely on so-called indirect methods to understand what planets orbit around stars. There's 2 main methods for this. It's the radial velocity method. So the idea is we have a star and then we have a planet that orbits this star. But this star-planet system, it actually does not orbit around the star. It orbits around its center of mass. Right? And this basically also means the star is actually moving towards us and away from us. And depending on that, we actually see a blue shift or a red shift of the light depending on the motion. So this is the Doppler effect. It's like when the ambulance passes by, right? So you hear the Doppler effect. Here we use it for light And with this Doppler shift, we can actually determine the mass and the position of the planet. The first exoplanet around the main sequence star was actually detected with this method nearly 30 years ago, and Michel Mayor and Didier Queloz actually received the Nobel Prize for this 5 years ago. So it's a very, very important discovery, and also indicates it's a very young field, right? If the first exoplanet was discovered 30 years ago, that's less than my age, so it's actually you know, a very young. Let's put it like this, okay? The other main method that we have is the transit method. You see the cartoon here, so the idea is we have a star, and then we have a planet that moves in front of it. And then as the planet moves in front of the star, you block the light from the star that can reach you. See this here? So this is the brightness as a function of time. So you have a very high brightness, but then the planet moves in front, and you observe a dip in your brightness as a function of time. And with this, you can actually determine the radius of the planet, because you can say, well, you have your stars, in that case, a circle. Your planet is also a circle, and then you can, from the areas, you can determine what is the radius of the planet. And this is the main method that was used in the Kepler Space Telescope, and currently in the TESS telescope, that is basically an all-sky survey to find close-in exoplanets. Now, if you actually have systems where we have both, where we can do radial velocity and transit, we can actually calculate the planetary density. We just make the assumption our planet is a nice sphere. We have mass, we have radius, then we can calculate the mean density. And with this, we can get some sort of indication about the composition of the planet, as you will see in a few slides. Now, with these main methods of planets, we can detect numerous exoplanets. So this is a plot of the detected exoplanets. So you have the planetary mass on the y-axis, and you have the semi-major axis on the x-axis. We have here our own Earth, we have Jupiter, and we have here Neptune of our own solar system. Now, these different colors, these different dots correspond all to the different exoplanets that we have detected so far, around 5,000 exoplanets that we have detected so far. The different color coding gives you the different detection methods that we can use to find planets. So I talked a bit about transit and radial velocity methods. This HR 8799 system, this was the direct imaging planet. You see from the color coding, this is mostly planets that are a few times the mass of Jupiter and very far away. And there's numerous other detection methods, but I will not go into the details of this, but I'm happy to discuss afterwards. But what you see in this plot is first you see that there are three main groups of planets that we seem to have. So one group up here, this is the so-called cold Jupiter planets, so planets of similar mass as our own Jupiter, and exterior to like 1 astronomical units. Here, in the close-in, we have also planets that are similar to the mass of Jupiter, but they're very, very close to the star. So this is 0.1 astronomical units. So they're even closer than that. So they orbit their star in a few hours to a few days. And these are the so-called hot Jupiters. They're called hot Jupiters because if you're very close to the star, of course, it's very hot. So it's a very imaginative. Down here, this group of planets here, they have a few times the mass of the Earth, or similar-ish, or a bit less than the mass of Neptune. So these are the planets that are called super-Earths or sub-Neptunes, depending on their composition. We'll come to that in a second. So we have different planets, but there's a big bias in this plot, because you can easily imagine that the planets that are bigger and closer to the star are easier to detect than the planets that are smaller and further away. So there's a huge bias in this plot regarding the detection of planets that are further away. If you were to do statistics of the planet occurrence rates, then these hot Jupiter planets they will not be the most prominent group. Actually, only around 1 to 1.5% of solar-like stars actually have a hot Jupiter. Instead, these planets down here, the super-Earths and mini Neptunes, they should exist around to like every third to every second star should actually have one. So there's a huge bias in the detection here. So it gets much harder to detect if you go down to this area. And you see there's not too many planets that we have detected that are below the mass of the Earth. So if you want to detect an Earth mass planet around the solar type star, this is still something we have to improve our instrumentation in order to actually achieve this. Now, as we indicated, we can determine if we have the mass measurement and the radius measurement, we can actually say something about the composition of the planet. So this plot is a bit confusing. Don't worry, let me walk you through it. So on this plot, what we have is the planetary mass in Earth masses, and then on the y-axis we have the planetary radius also in Earth radii. Now these dots with the arrow bars, these are the detected planets, and their color coding gives you the temperature, the equilibrium temperature of the planets. So basically it's an indication of how close to the star you are. So basically if you're reddish, you have a high equilibrium temperature, so you're very close to the star, and you go towards blue, you're a bit further away. Now, additionally to that, we can actually now run interior models of planets, where we say, let's make an assumption. We have a composition of the planet. Let's say in this case, for this red line, we have a planet that would be 100% made of iron. It's of course unrealistic to have a planet 100% made of iron, but let's just go into this assumption. And then if you have a given mass, we can actually calculate the radius of this planet. So for example, for like a 10 Earth mass planet, you would have around 1.4 Earth radius for the size of your planet, if you were 100% made of iron. On the other hand, if you go to like 33% iron, which is roughly the iron content of the Earth, so you see the Earth actually down here, and we have again also a 10 Earth mass planet, we would be around 1.7, 1.8 times the radius of the Earth. And then if you go even further up, so we can just follow this dark blue line, would be a planet that is 100% out of water. Of course also unrealistic, but let's just take a look. So if you have a planet, 10 Earth masses, that would be 100% out of water, you're around 2.5, 2.6 Earth radii. Now, with these lines, we can already say something about the composition of these planets. Of course, there's a very big degeneracy in this. So if you just have the mass and the radius of a planet, and you would have a planet that lies down here, well, you still don't know what is the real water content of this planet, because additionally to that, this planet could actually have a hydrogen atmosphere. So you see here, so this is the line we have just 2% hydrogen atmosphere, and the rest is an Earth-like composition. So if you have an Earth-like planet and you just add a little bit of hydrogen atmosphere, you increase your radius quite significantly. So you don't know if the planets up here, how much water they would have. If they have water at all, we would not know, but we know something about their density. On the other hand, if you have the planets that are down here, it's very unlikely that they would have a very high, large hydrogen envelope, because their radius is very, very small. So if they have some sort of atmosphere, it should not be a very large planetary atmosphere. Of course, again, for these planets, even though they would follow this 33% iron line, we don't know if they really have 33% iron, because you could just imagine, well, we have maybe a little bit more iron, but maybe then we add a little bit of water ice, so we don't fully know what their exact composition is. But we get a little bit of a feeling of what is actually going on for these planets. Now, additionally, this clearly implies we have a large variety of planetary compositions, but we can also learn something else of this plot. So if you follow here this diagram here on the right, that actually gives you the number of planets that we have to detect with the Kepler, so as a function of radius. So you see we have some sort of peak around 1.5-ish Earth radii, and you have another peak up here at like 2.4, 2.5 Earth radius, and there seems to be like some sort of kind of valley around 2 Earth radii. You also see this a bit in the plot. So the contour lines seem to indicate we have a clustering of planets here and a clustering up here, and there seem to be a bit less planets down here. And now we can actually look at this in a statistical sense. We'll come to that in a second. Before going into this, I first want to mention a little bit about the occurrence rate of planets as a function of host star metallicity. So what we have here is the planetary radius, so the size of the planet as a function of the metallicity of the host star, where 0 would correspond to a solar-like composition, and this is actually a log scale. So if you would be at 1.0, you would be 10 times enriched in metallicity of the planet, so in heavy elements that we can use to build planets. And then if you follow these red lines, there seems to be the trend that these larger planets are more probable to find around metal-rich stars. And this, to some level, of course, makes sense, because if you say we need a lot of material to build a giant planet, and if the star actually has more metals, more heavy element, it makes sense that this would be the planets that would form more preferentially around these stars. Now we can also look at the systems in themselves. What do the system architecture look like? So this is a snippet of some Kepler systems from the Weiss et al. 2018 paper, and we have here a bunch of planetary systems listed, and then you have here the Sol. So this is the solar system. So this is the 4 terrestrial planets of the solar system, and then what you see is that most of these planetary systems of these Kepler systems that you observe are compact planetary systems with multiple planets. So so this is Mercury up here. So most of these systems are actually interior to the orbit of Mercury. Additionally, what we see is that most of these planets within the same system, seem to have similar sizes and probably also masses. So of course, between these different systems, you see a difference, but within each system individually, there seems to be a similarity in sizes. And this led to the idea that this is like peas in a pod, where they all have, similar sizes and they're like well spaced. Now, of course, there's also systems where we have inner super-Earths and outer giant planets. And there's still a bit of a debate how frequent this is. So for example, Suan Wu 2018 claimed that basically every cold Jupiter should have inner super-Earths, while the other papers seem to indicate maybe not only every second. So there's still a debate what is the correlation between outer cold giant planets and inner super-Earths. And we will see later on why this is actually very, very important for the formation of these planetary systems. So the question that we have to always answer is, how can we explain actually this diversity of planets and planetary systems? To go back to the composition of these systems, we can actually plot here. So this is again the radius of the planet, and this is just the normalization fraction that we have. So in green, this is the data that we have from Kepler. And you see there's clearly a peak here around 1.3, 1.4 Earth radii, and we have another peak around 2.2 Earth radii. And the question is, how can we actually explain this? So we can first make the assumption, let's say all our planets have an icy composition, then we would arrive to this blue line. So we would basically have a minimum here that corresponds to the maximum that we observe. So clearly this does not seem to be the case. But if you say we have rocky planets, where we have rocky planets with no atmosphere here on the left, and if you have rocky planets that have some sort of atmosphere on the right, then we can actually reproduce this valley. But what does this actually mean physically? Physically, it means that maybe when the planets are born and they have some sort of atmosphere, and the planets are not big enough, they actually lose their atmosphere during their evolution. Could be like from stellar wind, from photoevaporation, that blows away the atmospheres if you're too small. But if you're big enough or massive enough, you can actually retain your atmosphere. So you can actually reproduce this valley. This works very well with this photoevaporation. It was first proposed actually by Owen and Wu 2013. Now there's a bit of a debate in the literature how deep that valley actually is and what the exact position of the valley is, but the idea in itself seems to be very, very robust in itself. There's another idea that we can explain this valley by some cooling of the core, where we can get rid of the water ice. But there's of course no overwhelming evidence for one of these two methods. And also additionally, we know of some super-Earths that we can actually observe that actually have a large water content. So it's still a bit unclear if it's really like one or the other. But my best bet is in that case, if you have the choice between 1 and 2, nature will always give you a mix. That's normally what will happen. So I think the best match that we can achieve for this observation is actually if we have rocky planets with and without envelope on both sides of the valleys, and probably also some water worlds that we can have. Now, how do we form these planets from a modeling perspective? So we start with a protoplanetary disk. So this is the TW Hydra disk. It's a close-by system around 40 light years. This is the micrometer-sized dust grains that we observed with the VLA. And then we can actually look at the same disk, but with ALMA, and we can see the millimeter wavelength. So these are the millimeter particles that we will call pebbles. This is the same disk, and this is the same size scale. Okay, so the micrometer disk is gigantic. The millimeter disk is a bit smaller, but of course still gigantic from our own solar system perspective. But we can actually interpret this as some sort of grain growth mechanism. So we have the micrometer-sized grains, and then these grow to millimeter-sized pebbles. So this is the birth environment of planets. We can of course also observe the full planetary systems at the end. But this is of course a journey over 13 orders of magnitude in size. So we go from the micrometer-sized grains all the way to giant planets. So we have to rely on modeling to overcome these 13 orders of magnitude in size. This directly implies, since we obviously cannot model each dust grain individually for obvious reasons, we have to rely on some parameterization for the different aspects of planet formation. And this is what I would like to talk to you a little bit about today. So what is the general framework of planet formation that we work in? So this is the so-called core accretion paradigm, where we have our star, and then we have our protoplanetary disk around it. And this disk, we have our small micrometer-sized dust grains. These can then grow to millimeter, centimeter-sized pebbles by coagulation or by condensation of water or CO2. And then these pebbles can actually make planetesimals. These are basically asteroids, so think of objects like 10 to 100 kilometers in size. Then by the accretion of asteroids, planetesimals, and pebbles, we can actually start to form planets. We can do small terrestrial planets, or we can build the cores of the giant planets that then have to accrete gas from the protoplanetary disk. Now, as these planets grow, they actually gravitationally interact with the protoplanetary disk. You see this here from a simulation. So we have our planet here, and you see this tiny spiral arm that the planet exerts. And with this spiral arm, the planet actually exchanges angular momentum with the disk and can move and migrate through the protoplanetary disk. Now, if your planet becomes a little larger, like Jupiter, you actually start to open a deep gap in the protoplanetary disk. So you push away material from your orbit, and then you have something which is called type 2 migration, which is much, much slower. Then we have to care about the disk evolution in this case. We have to then take all our models together and combine this to see what kind of planets we can form. We have to care about super-Earths. We have to care about the giant planets. And then we have to care about the composition, what these planets are actually made of. And this is all very, very confusing. And you can lose a lot of hair, as you see here. But the general paradigm, I'm absolutely convinced actually works out. There's of course a lot of different question marks, as you see here, and that's because there's still a lot of the detailed processes that we still do not understand and how they tie together. And the reason for that is related to the enormous difference in size, right? We go from the micrometer size all the way to the giant planets. So it's very clear we cannot do it in one simulations, and we have to rely on different pieces of simulations that study the different aspects of planet formation. For example, there's a lot of simulations that study how these small dust grains can grow into pebbles, and there's another set of simulations how these pebbles can grow into planets, another set how these pebbles can be accreted onto planets to form giant planets, how the planets migrate. It's all different set of simulations, and then we have to use these parameters and put them together in one step of simulations to really simulate the whole way. And of course, there's really some caveats in this model, but as naturally, we don't have quantum computing yet, so it's naturally very hard to avoid this. So what I would want to talk to you today is about a few different topics. So first, I would like to talk about how we actually model planet formation. So I want to explain the different steps that we have in here, and then I want to discuss a few questions that I think might be interesting, especially in the concept of habitability and astrochemistry, astrobiology, related to water in this case. So, for example, is the water ice then the birthplace of planets? Do the planets come from there? Can we constrain the formation location of these planets from their composition? How do the stellar abundances actually play a role into this? And then I want to ask how the giant planets can influence the inner system, and how we can then form maybe the small terrestrial planets also within our own solar system. So let's go. What are the tools that we need? Sometimes I'm as annoyed as to do these simulations as building IKEA furniture, but okay. Anyway, so how does this work? So we first have to understand the growth of these dust grains. So what you see here is a cartoon that is motivated by from experiments. So Goodler et al. They did these experiments where you have small dust grains. They put them in a cylinder in a drop tower or on the parabolic flight. They also had some experiments in the International Space Stations to understand how these small grains can actually stick in zero gravity environment. And what you see here is two columns. Where we have on this side we have two equal-sized particles, and on the right we have two unequal-sized particles. And there's different outcomes that these particles can have. So you can have hit and stick. So the particles hit each other, they stick and they grow. Or there's the other end. These particles hit each other and then they fragment. And of course, if you want to grow particles, fragmentation is very bad, because you want to grow something big, but instead you become smaller. And this fragmentation in itself is determined by the velocity at which these particles can collide. Right? You can easily imagine this. If you take your car and you crash into a tree driving too fast, you fragment your car. Right? It's the same process. So the problem here is this velocity of these particles. So generally speaking, larger particles have larger velocities, which prevent the growth above centimeter and decimeter sized particles. So I'll come back to that in a second, why this is happening. So if you become too large, you become too fast, and you fragment. So there's only a certain size that we can actually reach before we have to stop growing at this centimeter decimeter sized barrier. So how does this? Why is this the case? The reason is the particles actually move through the gas. So, and if you have a protoplanetary disk, you have our central star, then we have our disk around it. Then we actually have a radial pressure gradient in this protoplanetary disk. So we are hot and dense in the inner region, and we are cold and less dense in the outer region. So we have a radial pressure gradient in this disk. And now this radial pressure gradient actually supports the gas, the motion of the gas. So the gas in itself, so the azimuthal motion of the gas is actually supported by the pressure force. So the gas actually orbits on a slightly subkeplerian velocity. On the other hand, our small dust grains, they don't care too much about this pressure gradient, so they want to orbit on a Keplerian velocity. So what it means is we have particles going on a Keplerian velocity and gas that is slightly slower than that, which means we directly have a drag force that tries to rob these pebbles of angular momentum as they move. And in the moment you would lose angular momentum in the disk, you always go in. So just by the fact that we have a velocity difference, azimuthal velocity difference between the gas and our pebbles, the pebbles lose angular momentum and then they move inward. And this inward motion is actually much faster than the motion of the gas, a few orders of magnitude faster. And this has enormous consequences for the composition of the disk and for the composition of the planets. So to show this in a bit more detail, so this is a plot where we show the radial velocity of the gas and of the dust. And what we have here, we show this as a function of the Stokes number. So the Stokes number in itself is basically just a parameter that gives you something about the size. So if I basically put our micrometer sized particles here, so they have a very low Stokes number, they're coupled to the motion of the gas. It's like cigarette smoke, it follows the motion of the gas. But if you have larger pebbles, they actually decouple from the gas, and they would basically they spiral in much faster than the gas. So you see this here. So for these millimeter particles, if you have Stokes numbers of the order of 10 to the minus 1 or close to 1, we see we have a velocity that's a few orders of magnitude larger than the velocity of the gas. So our particles just shoot into the inner regions of the disk. Now, but what is the consequence of this inward motion? So the first question that we have to ask is what happens to the composition of these pebbles as they move through the protoplanetary disk. So in these simulations, we have particles that have different composition. They start in the outer disk at like 150 astronomical units, and then they move inwards into the inner disk. So if you just follow here, so you see the particle, the blue line, so the water line actually stays very constant as we move into the inner disk, and then we have this sudden drop in the water abundance of our pebble. And this sudden drop in the water abundance is because we go into the inner disk, and at some point the disk becomes so hot that water ice evaporates. That's why our pebble suddenly has no water ice anymore. But during the whole inward motion, the composition of the particle basically doesn't really change. So these different lines, line styles correspond to different drift velocities, where actually these dotted lines are the most realistic velocities. And you see also for the other molecules, the composition stays constant, and then in the moment you reach the respective evaporation front, we of course lose the volatiles into the gas phase. So the pebble composition is unaltered during the drift, which is, in my opinion, a very interesting result, because for once actually our life became a little bit easier. But the direct consequence of this is that we can actually enhance the disk with vapor in the disk. So you see this, so these here, so we have here the orbital distance in our simulation, and on the vertical axis you have the time, so the time evolution of our disk. So the color coding gives you the water content in the disk, normalized to the solar water content. In the outer regions of the disk, we have no water vapor, because the disk is cold and the water is in ice form. So we have no water vapor. In the inner disk, we have water vapor because the disk is hot enough that water ice evaporates. So what happens is in the beginning, our pebbles, they drift inwards much faster than the gas. They drift inwards and then they evaporate, and then the water ice becomes water vapor. But now this water vapor is of course a gas, so it's in gaseous form, so it moves much slower than the pebbles. This means, consequently, we can have a pileup of water vapor close to the water ice line, because water ice pebbles, they come in much faster, but we cannot transport the vapor away fast enough. So we get a pileup of water vapor into the inner regions of the disk. It takes some time for the gas, for the water vapor from the water ice line to make it all the way to the inner system. So we can enrich our disk by this inward drift and evaporation of pebbles. Now, this directly implies that the composition of the disk changes in time. And there's no way to just use some simple step functions to say like, oh, this is what the disk now, and that would imply that the disk was always like this. It changes as a function of time. But of course, we can actually calculate this inward drift, because the moment you would lose all your material in a very short time scale of, let's say, 100, 200,000 years, how can we still observe disks? The disks are millions of years old, but they're full of pebbles. What happens? What stops these pebbles? And this is what can happen in so-called pressure traps. So what you see here is a plot where we have the mass of our particle against the pressure support. So this is this eta parameter that is basically corresponds to the pressure gradient that we have in our protoplanetary disk. So here, if you have a small a negative pressure gradient, then we have basically our particles go in. So this is the red scale, so we move inwards. But then at some point, if we actually invert our pressure gradient, we can have a pressure trap and we can trap the particles. You can think about this. So if your particles go in, they lose the angular momentum due to the interaction with the gas, because the gas is subcapillarian. But in this pressure trap, what actually happens is that the gas becomes supercapillarian. So, and then of course you invert the direction of the pebbles. Now, if we have these pressure traps, we could probably retain the pebbles in these pressure traps. And this is actually what we think is actually happening in these protoplanetary disks. So again, this is the disk I showed you in the beginning. So we have these bright rings and these dark gaps. And the idea is that we have some pressure maxima where we can accumulate the particles. You see this in this old cartoon from 72. So what you have here is the gas pressure as a function of radius. And we see we have a pressure maxima up here, and the particles will always move to the point of highest pressure. So our particles accumulate in this pressure trap. And here at the pressure minima, we actually have no pebbles, so we can explain bright rings and dark gaps. So it's just pressure perturbations that we can have in these disks. I will come back in a second how these pressure perturbations could actually be caused. Now, well, as we said, we have these millimeter, centimeter-sized pebbles, and we cannot continue to grow them. But yet, we have to grow them because we have observed planets, we have planetesimals. There must be a way to grow them. And the idea here is that we have to concentrate particles, and then the moment we have a large cloud of particles, it can actually collapse under its own gravity and form planetesimals. There's different ways to concentrate these particles. So this is so you can have some small turbulence, some small eddies. Think of if you have a kind of a vortex where you accumulate your particles in the middle, and then there's the idea we have actually pressure bumps, as you see here, as we just discussed. And then there's another idea. This is so-called streaming instability, and the streaming instability feeds off the velocity difference between the particles and the gas, because as the particles lose angular momentum due to the interactions of the gas has to gain the angular momentum because angular momentum is conserved, right? And this means as the particles lose angular momentum, the gas gains angular momentum, and the velocity differences between particle and gas become smaller and smaller, and this means your particles actually slow down, and then the moment you slow down, you can accumulate more and more particles that come in from the outer regions of the disk, similar like a traffic jam, right? So you can generate a traffic jam, and there's some guy that just brakes a little bit, and then everybody has to slow down, and suddenly you generate a traffic jam. In a way, very similar to this situation here. Now, if you concentrate the particles big enough, we can collapse and make planetesimals that seem to have a characteristic sizes of around 100 kilometers in size. Now, the question is, where do these planetesimals actually form in the disk? Do they form everywhere? Do they just form a specific location? So we asked 4 authors for our PP7 review chapter, and they gave us 4 different answers, depending on their model. We can have some pileup of pebbles close to the ice line. So this is the blue result. The idea here is that we have particles of different sizes, interior and exterior to the ice line, that can then cause this pileup here. For comparison, this gray dashed line that corresponds to the minimum mass solar nebula. So the idea what the mass in our own solar system might have looked like. Then here in this model we just make planetesimals at the snow line. Here the idea is that we have particles in the disk, but as the disk evaporates away, you can actually your gas density decreases, and you can suddenly make planetesimals everywhere. And here in this model, the idea is that the disk is very turbulent. We have a lot of vortices in the disk, so we can accumulate the particles basically everywhere. So the point here is we have different ideas how we can make planetesimals, and the question that we have to understand is, do these ideas actually correspond to the planetary systems that we observe, right? So for example, in this model up here, we see we make a lot of planetesimals in the inner within 1.5 astronomical units, which probably is good if you want to make super-Earths, because you need a few Earth masses for each super-Earth. But it's probably bad if you want to make the terrestrial planets of our solar system, because you have like an order of magnitude too much mass. Then suddenly you don't make an Earth-like planet, you make a super-Earth of a few Earth masses. So it's still an open question where these planetesimals would actually start to form. We seem to know that this planetesimal formation would require like a minimum metallicity of minus 0.5. This is very interesting, because it also seems to be supported by the observation of planets. Because if you look at the super-Earth occurrence rate, they also find basically no planets that have a lower metallicity than this. So there seems to be some agreement between observation and theory, which of course is very, very nice. Now, how can these planets continue to grow? There's the idea you can of course accrete the other planetesimals, but you can also accrete these small pebbles. So you see this here in the cartoon. So we have our planet here, and then we have here in the dash, that is the Hill radius of the planet. So where the gravity of the planet dominates over the gravity of the star. Then we see here a pebble and the planetesimal are coming in. You see the planetesimal is mostly scattered away, and the reason for that is that you actually need to hit the gravitational cross-section with your planetesimal, which is much smaller than the Hill radius. On the other hand, the pebble can actually be accreted very nicely onto the planet, and the reason for that is because the pebble loses the angular momentum due to the interactions of with the gas. So this is basically the idea is our pebbles drift inwards, but then if you have a planet that sits there, the material can actually come to you. The accretion rate in itself for our core depends on the Stokes number, so on the size of the particles, depends on the Hill radius, so on how massive is our planet, and depends on the surface density of pebbles, so how many pebbles we actually have available. Now, this pebble accretion can only become efficient once our embryo is around the mass of the Moon, so a little bit bigger than the planetesimals that it can form. So we might need some initial conditions between these planetesimals to actually make these big cores, and then we can accrete the leftover pebbles and grow very, very efficiently. And the reason for that is why pebble accretion is so efficient is because we have access to the full mass reservoir of the disk, right? So your planet sits there, and all your pebbles, they just come to you. They lose the angular momentum with the interactions of the gas, and they just pass by. It's like it's like the rolling sushi buffet. You sit there, all the food comes to you, and you eat way too much. At least me. Okay, so you can accrete very, very efficiently these leftover materials. Now, on the other hand, of course, pebble accretion doesn't go on forever. At some point, you reach the so-called pebble isolation mass, which is the mass when your planet starts to open a gap in the protoplanetary disk. So you see here from a simulation our density field. So 1 is our initial density, blue means we have an underdensity, and reddish yellow means we have an overdensity compared to our initial density distribution. We have here our planet, and you see the planet actually opened a gap in the protoplanetary disk. Why did this happen? This is because of the exchange of angular momentum between planet and disk. So the inner disk gives angular momentum to the planet, but then if the inner disk gives angular momentum away, you lose angular momentum, so your inner disk moves in. At the same time, the planet gives angular momentum to the outer disk, and if the outer disk gains angular momentum, it moves away. So you slowly open a gap in the protoplanetary disk. And this is, of course, dependent on the mass of the planet, because that exchange scales with the planetary mass. And now this is an important consequence for the inward drift of pebbles. So you see here, again, so this is a plot of the azimuthal gas velocity in units of the Keplerian velocity. So 1 would mean we have Keplerian velocity. And this is on the x-axis, just the distance. So you see in the outer regions of the disk, our gas has this sub-Keplerian velocity, as we discussed in the beginning. Now, if a pebble comes in, it loses angular momentum because the gas is sub-Keplerian. But suddenly, exterior to the planet, we have this region where the gas is suddenly super-Keplerian. And this means instead of losing angular momentum in the disk, our pebble would actually gain angular momentum. So it would actually stay in this region exterior to the planet. But if our pebbles are up here and our planet is here, these pebbles cannot be accreted onto the planet anymore. And this means at some point the planet becomes so big, it starts to open a gap, and then pebble accretion self-terminates. So you cannot accrete the solids anymore. This whole process depends very strongly on the properties of the disk, like the aspect ratio, also the viscosity of the disk, but it also depends on the particle size as well, because we saw that the particles with different sizes drift differently through the disk. So the small micrometer sized grains could actually still make it through, but their contribution to the growth is very, very small, and it also scales with the stellar mass. So to iterate this a little bit more, so if you have a planet, a massive planet, we can actually open this very deep gap in the disk, and then we can generate this pressure trap exterior to the planet. So, and then this pressure trap, we would actually trap our particles. So this means we can have a planet where we have in its orbit basically no particles, and then we have this region where we have accumulated all these particles. Now we can of course, correlate this with our observation of protoplanetary disks. So you have these dark gaps, and then maybe if a planet is in this region, we have no particles, but then we have a pressure perturbation, and we can have these bright rings exterior to it. Now, of course, this means not all gaps, of course, have planets. This just means the planets is one way to actually open these gaps in the protoplanetary disk, because there are other effects that can generate these gaps, like zonal flows caused by magnetic fields or condensation at ice lines. But the planets can, of course, also do it. Now, how do we these planets? They, of course, these don't stay fixed, as I indicated. They actually migrate through the disk. This is a simulation where we have our planet here. You see the spiral arms, and these spiral arms actually exert a torque acting onto the planet. You can do the calculation. You can actually do this analytically. There's a lot of papers from the 70s and 80s that have done this, and you see that this planet then could actually move inwards into the inner regions of the disk on timescales that are much shorter than the lifetime of the protoplanetary disk. But if you include another effect, you can actually slow down the migration of the planet, and this is the so-called co-rotation torque. So the idea here is we have our planet here that sits in a protoplanetary disk where it's hotter and denser in the inner region and colder and less dense in the outer region. And this means for material that follows these horseshoe trajectories around the planet has some consequence. So the material that we have here in the inner region is hot and dense. Then it moves to the outer region, and then it will adiabatically. So it's hotter and dense here. Then we move to the inner region where the disk is colder and less dense. So our material will adiabatically expand. So we will generate an underdensity behind of the planet. On the other hand, the material that comes here from the outer regions is colder and less dense. It goes to the inner regions, and then where it adiabatically compresses, so we get a high density region. Now, if you have a high density region in front of the planet and a low density region behind of the planet, these regions actually exact a torque onto the planet that can actually move the planet outwards. So you can actually change the direction of migration. Depends also a bit on the orbital parameters like eccentricity and inclination. But if this exchange of angular momentum is very efficient, you actually open deep gaps in the disk, and then you migrate on a so-called viscous timescale on the disk, so the migration becomes much slower. Now, the growth of the planets after the pebble isolation mass continues, so we can actually start to accrete gas onto our planet. So you see here a picture of the mass evolution as a function of time. So we first start to form our planetary core, then we grow our core, we have maybe already some primordial atmosphere onto the planet, but then our planet, as it continues to accrete, we actually pollute the atmosphere. So as the small pebbles come in, they might not make it directly to the core, but they might actually evaporate into the primordial atmosphere. So you have a very heavy element-rich atmosphere just from the accretional heating, and then at some point we can, if we become big enough, we can go into this runaway gas accretion phase and become a gas giant like Jupiter or Saturn. Or if we actually fail and we don't go into this runaway gas accretion regime, we can become a super Earth planet. We might lose some of the atmospheric composition. So this whole growth phase for the gas accretion depends how efficient your planet can actually contract. So in the contraction, of course, is a function of the mass of your planet, but also a function of the opacity. So basically, the question is how efficiently can your planetary cool in order to start to contract. Additionally, the gas accretion we have seen is actually really a 3D process where you can have streams that come from the upper layers of the disk. You can expel them through midplane. Magnetic fields play a role. So it's a very complicated topic that requires detailed simulations. So I will not go much more into the details, but I'm very happy to discuss afterwards. So we actually have all our tools ready to build planets. So let's take a look at the different questions that we have to ask for our topic. So we're first interested in, is the water ice line actually the birthplace of planets? For example, also in our own solar system, because the question is why is the water ice line actually special in this case? So first, let's take a look at the previous simulation. So this is the minimum mass solar nebula, or Hayashi nebula. So what we have here is the surface density, so the vertically integrated density as a function of radius. So the idea of this minimum mass solar nebula is you take the solid masses of the planets that you have, you smear them out in a ring, and then you get the surface density of this at that region, and then you multiply with 100, and then you get your gas surface density. And what you see here, you have a jump in this surface density, and this is related to the idea that in the inner regions you just have rocky material, and then suddenly you have also ice, so water ice. So that's why you have this jump here in the minimum mass solar nebula. So you would have also icy particles in the outer regions of the disk. So the question is why could that actually cause the growth of the planet? So the idea here is that these materials that are in the outer regions of the disk could actually be larger than the materials in the inner disk, and that can change, first of all, the drift of the particles, and therefore also the way they can form planetesimals, and it can also change the disk structure in itself. So you see here in this simulation, so this is the evolution of the snow line as a function of time, and then you see that we have some regions where we can preferably make planetesimals. So the idea here is that we have a pile-up of material close to the snow line, because these authors said that the particles in the outer regions where we have water ice could be a bit bigger than the material in the inner regions of the disk, so they drift fast, and then you kind of generate a traffic jam at the water ice line. So you pile up material, and then you can start to make planetesimals in this region. But it also changes the structure of the protoplanetary disk. So you can imagine a disk. We can just assume we have an opacity in the disk, and the opacity of the disk would determine the cooling rate. So the cooling is proportional to 1 over the opacity. Now, if you make an assumption about the opacity, we can take the cooling, and then we can calculate the disk structure. So this is what we did in the past. So what we have here is the temperature structure as a function of orbital distance and as a function of time. So in black, that would be our initial conditions for a given surface density that we have, and then as the surface density reduces in time, our disk becomes colder because we reduce our viscous heating. Now, in the outer regions of the disk, we would have icy particles. In the inner regions, we have our non-icy particles or silicate particles. You see there's some structures going on in this region of the disk, and this is because there's actually an opacity transition between the rocky and the icy part. Now, other sets of simulation decided, well, we start with a given disk structure, and then we can calculate the velocities of the gas, and with the gas velocities we can calculate the pebble sizes, so we can calculate the grain size distribution. As you see here, so we go from small particles to large particles, then we have some sort of grain size distribution, which gives us an indication about the grain distribution in the protoplanetary disk. However, the grain sizes determine the opacity, right? So you see here, so this is a plot where we show the Rossland opacity as a function of temperature. So these different colors correspond to different particle sizes, and I think it's very clear to see that, like the millimeter particles, they have a much lower opacity than the micrometer sized particles. Additionally, this grain line here corresponds to the water ice line. So in these regions here, in the cold regions, we have water ice and silicate particles, and here we only have silicate particles. So you see a jump in the opacity at the water ice line. So what we then decided to do as well, we have to actually complete the whole loop. So we decided to do some simulations where we say we start with an initial grain size distribution, calculate the opacity, that gives us the disk structure, that gives us the velocity, that gives us the new grain size distribution, and we iterate until we reach an equilibrium for this. This is what we did in the past. But now there's a twist to it, because the idea here is that water ice grains and silicate grains might actually not have the same size. So this is motivated by experiments from Gundlach and Wurm nearly 10 years ago, where they looked in laboratory experiments how grains can actually grow in the lab, and they found that particles that contain a little bit of water ice can actually grow more efficiently, so can grow to larger sizes. If you want a stupid analogy, imagine you go to the beach and you want to build a sandcastle, and if it's completely dry, your castle will just collapse. But if you have a little bit of water, it sticks a little bit better, and then you can actually grow more efficiently. But recently this has also been put a bit into doubt, because these experiments with ices are very, very tricky to do. So let's go into this in the assumption that our water ice grains can actually grow larger than the dry silicate grains. So what that means is we have a change in the so-called fragmentation velocity. So that's the velocity the grains can reach before they start to fragment. So if you have cold temperatures, we could have larger grains, and if you have higher temperatures, we would have smaller grains. So our fragmentation velocity changes. And this directly implies that we go from large grains to small grains as our disk becomes hotter. So the question is, what is this effect actually on the disk structure in itself? So we can here look at this in the cartoon. So we have our ice line transition here. In the outer regions of the disk, we have our large icy particles, and in the inner disk, we have small silicate grains. And this means we directly have a transition in opacity, right? You remember these larger grains, like millimeter, centimeter sized grains, have a much lower opacity than the micrometer sized grains. So we have a transition in opacity of our protoplanetary disk around the snow line. And now we can actually, if we put this into our simulation, what does this actually imply for the structure of the disk? And this is what you see here. So first we have here the aspect ratio of the disk, essentially a measurement of the temperature as a function of orbital distance, for three different sets of simulations. So we have here with a fragmentation velocity of 1 meter and one of 5 meters, and then this solid line corresponds to a transition where we have a small 1 meter per second transition in the inner region and 5 meter in the outer region. So we have a lot of small grains in the inner region and bigger grains in the outer regions of the disk. But this directly implies that there has to be a change in the disk structure, especially in the disk temperature, right? So if you have different grain sizes, it actually means we have different opacities, and then this means we have different coolings of the disk, but actually this, the temperature and the aspect ratio, they are related through this formula. So if you have the large grains, we have a low opacity, so we have an efficient cooling, so we have a temperature drop. And in the inner regions, we have a higher opacity, so we have a less steep temperature change. So we have this very steep gradient in temperature. But this very steep gradient in temperature directly gives you a gradient in the surface density of the protoplanetary disk. Because the assumption is we have a constant accretion rate through the disk. So the accretion rate is the same at all radial positions. And then we get a transition. We have to get a transition in our surface density because the aspect ratio that we have here actually feeds into the viscosity. So there's so the viscosity is proportional to our aspect ratio. So if you have this change in temperature and thus in the aspect ratio, we have to get a change in our surface density. And now if you have this change in our surface density, it directly implies we have a change in the pressure gradient, right? Our radial pressure gradient changes because of this. And you see this here, this is a radial pressure gradient. So our dlnp that we use for the inward drift of pebbles as a function of distance. We have here the position of the water ice line. You see if you have this transition, we have a spike in our pressure. So we have actually a position where we could actually accumulate pebbles at these regions of the disk. Now, this also implies we could actually trap planets in there because the migration of the planets also scales with the disk parameters. So if you have this very steep increase in the surface density, we can actually generate a planet trap. You see this here. So this is color coding the torque acting on the planet. So red means we have a positive torque, so meaning we migrate outwards. You see here, so this is the position of the water ice line in the simulation. We see we are very red region. So our planets would actually stay in this region, which is great. So the pebbles stop. We have material there. We make a planet, and the planet actually doesn't move away from this zone. It actually stays there and can accumulate and grow more and more pebbles. So that seems to indicate that the water ice line could indeed be the birthplace of planets. Of course, it cannot be the birthplace of all planets because if you make planets close to the water ice line, they would probably contain a lot of water, and you know the Earth doesn't have that much water. So you certainly cannot form the Earth in this way. But it might be an option if you look at giant planets. Now we can wonder, well, if we have giant planets, is there actually a way where we can constrain where these planets actually came from? Did they come from the water ice line or from somewhere else? And the idea here is that we go into the atmospheric abundance of these planets, because the idea is if you measure the atmospheric abundance of a planet, it can maybe tell us something about the formation location. So what we have here is two planets, WASP 77AB and Tau Boötes b. These are two hot Jupiter planets. And we have measurements of their carbon and oxygen content. So these are these squares. You see there's some error bars attached to it, but you can already see there's a difference in the carbon and oxygen content of these two planets. So one is actually supersolar, the other one is subsolar in composition. But the C/O ratio of both of these planets seems to be rather similar. Now the question is, where did these planets actually form? So the idea here is we run a lot of simulations where we have planets that are growing and migrate through the disk, and then we can check their composition from our simulations, and then we compare this to the composition that is observed. And this is what you see here. So these are so-called growth tracks. So we have the growth of the planet. So in solid line corresponds to pebble accretion. And then the dashed line corresponds to the gas accretion phase. So you have planets that start at different positions in different disks with different viscosities. So the viscosity determines how fast you can migrate and how fast you can grow. And what you see is that these planets, as they grow, they actually migrate through the disk, and then they cross different evaporation fronts. So you see this is the lines that are indicated here. So for example, we have here the water evaporation front. Now if your planet is in the outer regions of the disk and it grows, then during its core growth it can accrete water ice, because the water ice is trapped in the pebbles. You accrete the pebbles and you can happily accrete them. But then the moment you start to transition into gas accretion, you open a gap and then you accumulate your pebbles exterior to your planet, and this means you trap the water ice exterior to your planet, and this means the water ice cannot be accreted onto your planet anymore. And then as the planet grows here, you cannot accrete water, especially not water vapor, because you don't have water vapor yet. But then the moment you migrate across the water ice line, suddenly you can accrete the water vapor, right? Because the water ice that you could not accrete in the pebble form now evaporates, and you have water vapor, and that water vapor can be accreted onto the planet. So the point is, depending on your position, your planet will have a different composition, because the planet in the inner regions of the disk, they will be very oxygen rich because you can accrete a lot of water ice, but the planets in the outer regions of the disk, they might be very water poor because you cannot accrete the water vapor. So this is just some small sets of simulations, but of course you have to test many different parameters and many different simulations to constrain this planet formation location. And this is what we did. So this is our best match result, so to say. So again, we have the square boxes for our observations, and this dot corresponds to our simulations. So first of all, our model seems to be successful in getting a supersolar and subsolar carbon and oxygen ratios, which is great. So we can already explain these trends. We fail a little bit with our carbon contribution, but we'll come back to that in a second. So what we could conclude from this is that these planets actually formed at slightly different locations. So WASP-77AB, it's a subsolar in carbon and oxygen. So in our model, it would form beyond the CO2 evaporation front, while Tau Bötis B, it is a supersolar in carbon and oxygen, and then it would form beyond the water evaporation front, so interior of the CO2 evaporation front. So Tau Bötis B, at least in our model, accreted a lot of CO2 vapor. So we can, to some level, constrain the formation location of these planets by looking at the abundances of these planets. I think it's very important to note that the C/O ratio alone would not tell you the story, because these two planets, they actually have the similar C/O ratio. Yet, and if you would just look at the C/O ratio, it would actually imply that both of these planets would form in the similar regions of the disk. But we can actually break this degeneracy by looking at carbon and oxygen separately. Now, how does the stellar abundances influence this whole picture? The idea here is that, of course, every star is different, and every star has a completely different composition. So what you see here is on the x-axis the iron abundance of stars, of solar-type stars in the neighborhood. We measured this in we used the Galan survey for this, and then we have here the different elemental abundances of carbon, oxygen, magnesium, and silicate, as you see here. There's some error bars in this. But it also means, so the first thing that you can take away from this plot is, of course, that the different elements scale differently due to the galactic chemical evolution, which, of course, makes sense. But then, of course, we can actually plot the individual composition of our stars. So this is what you see here on the right. So this is, again, the iron abundance on the x-axis, but on the y-axis, we have the C/O ratio of the star, of all the stars in our sample. That we have. So all these dots correspond to stars. You can kind of follow this black line. So there seems to be some sort of trend with the C/O ratio, with increasing metallicity. But the point here is you see that the C/O ratio varies a lot, right? So if you have a star and you just know the iron content of the star, you don't know what the oxygen and carbon ratio of that star would be. And the question is, of course, what does this actually imply for the chemical composition in disks and also for planets? So let's take a first look for the building blocks of planets. So this is what we calculated here. So you have these different colors that correspond to different solids, but I would like to focus here on the blue line, which is the water line. So as our host star metallicity increases, our water content, so this is the blue line, goes down from a mass fraction of around 50% down to just a few percent. And the reason for that is that because of the increase in the carbon over oxygen ratio, right? So carbon over oxygen increases with the host star metallicity, and this reduces the water content because the carbon actually binds the oxygen mostly in CO and CO2, which means we have less oxygen available to form water. So our water content goes down as we increase the metallicity. Now this has consequences, of course, for the formation of planets, for their growth and for their composition. So we have here a simulation where we grow our planets by accreting pebbles. So all these planets start at the same initial position, but they follow different initial metallicities as you have. So for the blue line, initially blue line here as a subsolar composition of -0.4. So we have a very large water content, 50%. You see the planet is blue, so very large water content. As the planet crosses through the ice line, of course, we don't accrete water anymore. And then we have some water content of like 20-30% in the inner regions of the disk. On the other hand, the planet that forms in the metal-rich environment, so at Fe over H 0.4, is the red line. So we grow in the outer disk and we always have a very, very low water content because we basically have no water available. So in the end, what we make is a planet that is very, very water poor. So basically by changing the composition of our disk, which inherently comes from the composition of the star, because we make the assumption that the stellar composition that we observe is a tracer of the initial disk composition. We change the growth and the composition of the planet that we can grow. So it clearly seems, in my eyes, there's a clear indication to go beyond just the FE/h for not only for planet formation simulations, and also for the composition and also for the occurrence rates of planets, because I think there might be something else hidden in there that goes beyond the classic FE/h abundance that we look at. And additionally to this, is super important for the composition of planets, right? So again, this is the C/O plot. As a function of metallicity. As I said, the initial stellar composition corresponds to our disk initial composition. But now let's take the exercise and take a star where we have FE/h 0, but we have completely different C/O ratios. Then we can calculate the composition of a planet, of 2 planets that would form at 3.5 astronomical units. And then you see here, so these are the 2 results of the 2 simulations. Once where we have a C/O ratio of 0.87, and here we have a C/O ratio of 0.35. And you see these dots, again, are the results from our simulations, and these squares were the results from tau Bötis B from the observations, right? So and it directly indicates, even if you say you have the same FE/h, by just changing the C/O ratio, you completely change the result of your simulation, which of course makes sense, because the C/O ratio sets how much water you have, how much CO2 and so on you will have. So without the detailed stellar abundances that we can use as input, we cannot play the game of constraining the formation pathway of planets. So the stellar abundances are super important if you want to understand something about the formation location of these planets. Additionally to that, we can look at the water content. What you have here is the water mass fraction in stars, calculated with the same type of model as a function of whole star metallicity. And this is the alpha element content, so like magnesium, silicate, oxygen, and carbon. And these dots correspond to stars, so solar type stars in our neighborhood. You see, again, there's a decrease in water content as we increase our FE/h, which is basically what we had in the previous plot. But on the other hand, you also see there seems to be some sort of, especially if you go down here, there seems to be some sort of vertical trend in here, where maybe these stars up here would have a higher water content. They are enriched in alpha elements compared to the stars that are down here. And why is this important? It's important because if you look at the occurrence rate of giant planets, so this is what you see here. So we have here the again whole star metallicity, and this is the mass fraction. So the fraction of stars that harbor giant planets. And you see here this increases as you increase this metallicity. So we can, of course, explain this. More metal-rich stars have more material available, so it's much easier to make planetesimals. It's much easier to accrete your cores and to make giant planets. But the question is, if there's a trend that actually goes here in the vertical direction, right? So this diagram here corresponds to the x-axis, but is there still something missing in the vertical direction? Like, for example, are these planet host stars always hosts that are like on the upper part of this diagram or on the lower part of the diagram? Because that will tell us something about their formation, but this is something that is not studied, at least to my knowledge, yet. Now, I would like to change gears a little bit. So the question is, how do giant planets actually influence their inner system? So we've heard that giant planets can actually have inner super-Earths. But the giant planets, they also open gaps in the protoplanetary disk. And if you open a gap, you change the flux of the pebbles. And this is what then might actually change the composition of inner planets. So we have here our protoplanetary disk. So we have our star, we have a disk around it. In the inner disk, we have water vapor. In the outer disk, we have water ice. Now, in a first scenario, we can think of the idea that we have a giant planet exterior to the water ice line, so it would reach the pebble isolation mass and would block the pebbles exterior to it. And then these water ice-rich pebbles are blocked. They cannot reach the inner disk. They cannot release their water vapor. And then our inner disk region might actually be dry. So if you make a sub-Neptune planets in the inner region of the disk, this planet might actually be dry and have a very low water content. On the other hand, if you have a giant planet interior to the water ice line, you would still block the pebbles, but these pebbles would actually lose the ice component. So the water vapor is still released into the disk, and the water vapor can actually pass the planet, and you would generate a wet inner planet. So that can accrete water vapor from the inner regions of the disk. On the other hand, there's of course the third scenario. We have a planet, we make it in the outer regions of the disk, it can accrete water ice, and then you just migrate in and we would have a very wet sub-Neptune. So we can have an increase of the water content for these three different scenarios. Now the question is, what does this tell us? Right, so the formation time of this giant planet and position it seems to be the key to the water content of the inner planet. Now, if you have a giant planet in this scenario exterior to the ice line, we might have a dry Neptune. If you have the water giant planet interior to the ice line, we might have a wet Neptune. Now, there's this idea in the solar system that Jupiter might have formed early and then stopped the material from the outer regions of the disk to reach the inner regions of the disk. And now we can actually use this idea for exoplanets, and now think if there's some scenarios where we can actually see if this early formation of Jupiter might actually have happened in other systems. Because if Jupiter forms early and exterior to the water ice line, we should observe dry planets, and if Jupiter forms interior to the ice line, or maybe even late, then most of the material already made it to the inner disk, we would still have wet inner planets. So this is the idea that we want to focus on. So we can look actually at systems. There's actually surprisingly not that many systems where we have well-constrained inner planets and that have an outer giant planet. So this is again planetary mass against distance, against their radius. The different colorful lines correspond to the line of different compositions, and these dots are the different planets that are detected that actually have outer giant planets. So you see the outer planets, giant planets here. So their mass is a function of distance. These vertical lines correspond to the different positions of the water ice line, and you see there are actually some systems where we could have outer giant planets that are exterior to the water ice line, and now we have to relate them to some of the planets in here. There's actually only one planet in there, one system in there that has an outer giant planet, and a planet that actually contains an atmosphere that we can actually measure. So this is the HAT-P11 system. There's actually a measurement already of the water content of this planet, which seems to be subsolar, and we tested our model. And it actually implies that the giant planet will actually have to form early in order to block the water ice efficiently in order to generate this planet with a subsolar water content. So it seems to indicate, at least from one data point, that giant planets should form early-ish. But again, of course, it's only one data point. But there's another system that is actually in the GTO time of James Webb, so we're very excited to see what will happen. Now we can bring this actually together to understand our own solar system. So what is the role of Jupiter in our own solar system for the terrestrial planets in this scenario? So we can first talk a little bit about the materials of our solar system. So we have Jupiter, we have the Earth, and we have Mars. And then we have the asteroid belt, as you see here, and I will just divide the asteroid belt very simplistic into two regions. So we have the carbonaceous chondrites, which are the water-rich, that's why they're blue, and we have the red. This is the non-carbonaceous, which is the water-poor. And then if you follow talks from these communities, from the cosmochemists, I think this is the only thing that they agree on, that the blue is the water-rich and the red is the water-poor. I think this is really the only thing that they that they mostly agree on. Okay, good. So we know the Earth is relatively dry, so we cannot accrete too many water-rich materials. So additionally to that, we know that there's some isotopic dichotomy between the inner and outer solar system. You see this here in this plot. So this is chromium against titanium. So in blue we have the carbonaceous chondrite group, and then in red we have the non-carbonaceous chondrites. We see the Earth, Moon, and Mars sits very happily in this non-carbonaceous group. Now the idea could be that we have maybe some mixture. So maybe if we make the Earth from anstatite and ordinary chondrites, maybe we can add a little bit of carbonaceous chondrites in order to move to the position where we are. In any case, there's a clear dichotomy between these. And the question is, what could cause this dichotomy of these two sets of material? So this is an idea that was put forward by Kreuer 2017, where the idea is, well, as our system grows, so this is the time in the vertical direction, Jupiter's core grows, and then we start to open a gap, and we block the blue material exterior to the to Jupiter, and we cannot mix the blue and the red material, and then we have this isotopic dichotomy. Now, in their model, we see that Jupiter actually formed around like 1.5 million years. But the problem is that this is 1 million year, 1.5 million years, actually very, very long time, considering how fast pebbles can actually drift through the protoplanetary disk. So what you see here in this simulation is the time evolution of the mass for the pebbles and planetesimals in the inner and outer regions of the disk. So let's just focus here on the inner region, so the terrestrial planet zone. So we have first a lot of pebbles that drift into the inner regions of the disk. So during the first few 100,000 years, the pebbles drift into the inner disk. We can enrich the disk with large amounts of pebbles. This means we can make a large amount of planetesimals. And you see here, towards the end, after like 1 million years, you already have like 20-ish Earth masses of planetesimals in the inner regions of the disk. But this is a problem, because 20 Earth masses of planetesimals is too much to make the terrestrial planets. The classic simulations indicate that you need like 6 Earth masses of material in order to make the terrestrial planets. If you have more than that, you would actually make super Earth planets. So if you just say Jupiter formed at like 1 million years and cuts the pebble flux, it's nice, but it's too late, because you make too big of a planet. Because as nice as, of course, the cosmochemical constraints with isotopes are, I personally think the mass of the Earth is also very, very big constraint. So if you have too much material in the inner regions of the disk, you make super Earth and not an Earth mass planet anymore. So there must be a way to cut the pebble flux earlier. Now, from a formation perspective, it is very difficult to actually make giant planets in much, much shorter times. But we can actually look again at the protoplanetary disk. So this is an observation of a young protoplanetary disk, IRS 63. And by young, I mean this disk is just a few 100,000 years old. And you see, nevertheless, that there's some structures in the disk. So we have bright rings, and we have gaps in this disk that's just a few 100,000 years old. And this indicates that maybe this blocking of pebbles could actually start very, very early. The reason for this gap opening could be some pressure perturbations in the disk that can be caused by infall, by magnetic zonal flows, or by transitions at the ice line, as we saw earlier. So there's a way to slow down the influx of pebbles. So this is what we looked at in our model. So we have a protoplanetary disk. So this is the gas surface density as a function of distance. And we have some pressure perturbations in the disk. So we have here the pressure perturbation at the water ice line, the CO2 and CO ice line. The different colors give you the time evolution of the material. So this is the gas surface density. We have these different pressure perturbations. Now, in these pressure perturbations, we can actually pile up our pebbles, right? So the pebbles pile up in these pressure traps, as you see here, as a function of distance. So each of these pressure traps would pile up pebbles. Now, if you pile up the pebbles, you can actually make planetesimals. And this is what you see here. So we have our 3 different regions of where we accumulate pebbles and where we can then make planetesimals. And these 3 different regions correspond roughly to the 3 different regions for the planets. So we have the terrestrial planets, where we have like 3 Earth masses of planetesimals to make the terrestrial planets. We have like 80-ish Earth masses of planetesimals to make the giant planets, like Jupiter and Saturn. And then we have something in the outer regions of the disk that could correspond to the Kuiper belt. Now, the asteroid belt, as you see here, is mostly empty. The idea here is that as the planets grow, they can actually fill this inner empty region. It's the same thing like, if you have a small baby and it starts eating solid food, some food goes in and gets secreted, but there's a lot of scatter, right? This is planet formation is planetesimals for you, okay? So we have material from the inner region that gets scattered into the asteroid belt, and we have material from the outer region that gets scattered into the asteroid belt. And this can then explain the distribution as we had before. Now, additionally to that, we can actually reproduce the small mass of Mars. So these colorful dots are the terrestrial planets in our solar system, and the gray dots correspond to our simulation. So we get this kind of shape. So we have large Earth and Venus and a small Mars. Additionally to that, if you look at the source region of the material that the planets ingested during their growth, we see that Venus and Earth have a different zone where the mass comes from compared to Mars. And this is great because Mars and Earth are actually a bit different from the isotopic composition. So this is very nice. Additionally, we can now put this together in a cartoon form. So we have our initial idea where we have start our planetesimal formation at these different sublimation lines. So we have our silicate sublimation line, the water line, and our snow line. We make our planetesimals in these regions. As the disk cools, these planetesimal production lines move inwards. And then in the inner regions, we make our non-carbonaceous. We have our non-carbonaceous chondrites, so we make our terrestrial planets. As they grow, they scatter into the asteroid belt, and as the giant planets grow, they scatter the carbonaceous chondrites into the asteroid belt. So basically, fill the asteroid belt from both sides in this model. But this is not the end of the story. Because I was just discussing some isotopes where you can think like, oh, maybe mixing actually makes sense. But the problem arises when we talk about molybdenum. So this is molybdenum against zirconium, and you see here in blue, this is the carbonaceous chondrites of the outer solar system. You have ordinary chondrites, ansatite chondrites, and you have the Earth sitting there, and you realize the Earth is an end member in this scenario, which means you cannot explain it by mixing any of those. Right? So if you mix any of those, you will never arrive at the composition of the Earth. You just cannot. So the question is, what's going on here? And there's a few ideas that are going on. So one idea is maybe there's a lost reservoir in the inner regions of the disk that maybe we should need to sample from Venus and Mercury, but we unfortunately don't have data from there because all the meteorites that we get, they mostly come from the outer regions, because from a gravitational perspective, it's very unlikely that something actually comes from the inner regions. And so and another idea is actually the question of the accretion efficiency of the material, because you can imagine, as you have a planet that is growing, the planet is very, very hot. But then if you have small pebbles that come in, they could actually evaporate in the upper layers of the atmosphere, and then they might not be accreted but transported away by recycling flows during the protoplanetary disk phase. So even if you would accrete material that has a different composition, it does not mean if you have material from some composition that goes into your planet, it does not mean that your planet will directly get this composition. So it's still an open question in the community how we can explain this, and I'm very, very curious to see how that will work out. So to summarize, there's a few things that I would like you to take home. So the first thing is everything in the disk moves. Gas, dust, pebbles, planets, everything moves. There's nothing stationary in there. Giant planets can cause the gaps in these disks, but they do not cause all the gaps, and there's not all gaps can actually harbor these planets. The flux of the pebbles, so how much material we have available, actually determines the formation pathway and the outcome of planet formation. So if you have a lot of pebbles that go into the inner disk, you can grow bigger planets, and if you have less material, you can grow less big planets. We might imply an early pressure bump formation to explain the solar system's inner structure, to explain the growth of the planets, and also to explain the isotopic dichotomy. But again, I think there's a very nice relation between the exoplanet research and the solar system, because as I showed you, we have of course systems where we have giant planets around other stars, and then the composition of their inner planets can maybe tell us something about their formation pathway, and you can try to see if that all plays together. Additionally, I think water plays a vital role for the formation of planets. First, we can trace it very nicely in the composition of exoplanetary atmospheres. We can trace it in the composition of protoplanetary disks. The water ice might be the birthplace of these giant planets. So I think water is very essential, and of course, it changes as a function of the stellar mass. Then in case something unrelated, so in case you actually are interested in this planet formation and disk evolution code, we actually made it publicly available. So you can just look here, there's a link to the GitHub, there's an instruction manual that you can just download and run the code. It's fully written in Python. for the younger generation that likes Python. If I had my word, it would be Fortran. But anyway, you can download the code, or if you have any questions and you just want to do it later on, just shoot me an email and I'm happily answering those. And obviously, I'm very happy to answer any other questions related to this right now. Thank you very much.